Good morning to all the participants. I, Unnati Shah, working as Assistant Professor in Electronics and Communication Engineering Department in Parul Polytechnic Institute, Parul University, Vadodara, Gujarat. Welcome all the participants in their today's webinar about RF antennas using EM simulator FEKO. Also, I would like to welcome our today's speaker. On behalf of Parul Polytechnic Institute, Parul University, big welcome to Mr. Kartik Gohel, sir. Mr. Kartik Gohel is a technical expert with a diversified knowledge of electromagnetic solution, currently employed at Design Tech Systems Private Limited, Bengaluru, working with the team of Altair FEQ. Prior to this, he was associated with Jyoti Electronics, Ahmedabad, handling CST Studio Suite. He also has vast experience of handling academics as an assistant professor while connecting with SRMS Trust institutions. He has published multiple articles and research papers in different journals and conferences of high national and international importance using different EM simulators like Keysight, ADS, and ANSYS HFSS. So welcome, sir. Without wasting much time, we are starting our session. Over to you, sir.
Thank you, ma'am. Thank you for the brief introduction about me, and thank you for inviting me for this particular webinar series. Just acknowledge when my screen is visible to you, ma'am.
Okay, sir. Yes, sir. It's whole visit.
So we are into the slideshow mode now. And
Ye-
firstly, a very World Environmental Day to all the attendees over here. It's 5th June, and we celebrate Environment Day today. And because we are onto a particular subject called antennas, which somehow has some impacts over our environment on a very large scale, so we would be considering that factors as well. So I'll not be going into that part of antennas today. Usually I talk about 5G and 6G antennas, but I'll not talk about 5G antennas and 6G antennas today because yeah, we are celebrating Environment Day today. So before going into the major antenna class that I'll be demonstrating to you guys, I was told that there would be the graduates, undergraduate students, as well as some polytechnical students who would be having a brief knowledge about electromagnetic field theory, who would be knowing few of the antenna class elements. So keeping your understandings, keeping your basic concepts, I'll be showing you few of the antennas that you might be knowing in prior. You would be knowing a wire antenna, that is a monopole antenna. You would be knowing some horn antennas. You would be knowing some patch antennas. So we would be talking about all these. But before that, let me give you a glance of my organization with which I used to work. Like I'm currently employed at Design Tech Private Limited at Bangalore, but we work in close proximities with Altair Engineering. And Altair Engineering was founded in 1985 and has multiple users all around the world. As of now, we are having 5,000 customers globally, which includes around 60K of users, and the number is going on increasing day by day. These are the few customers we have around the world and around in our country as well. All the DRDO labs, all the private industries working in electric vehicles, working in communication sector, working in aerospace sectors, all are using our tools massively. So now switching to this particular tool called FECO. FECO is nothing but an electromagnetic simulator which takes care of the electric fields and magnetic fields over a particular geometry. And you all might be knowing, I'll not be going in much details of the complexities of the tool because you will not be able to catch that because of the understanding levels you people have. So electric field and magnetic field, we people understand very easily. And what we understand with this, that there should be some Maxwell equations, like Maxwell equations. We have 4 Maxwell equations: Gauss laws, electrostatic Gauss law, magnetostatic Gauss law, and Ampere circuit law. We have these sort of Maxwell equations, right? So these Maxwell equations are utilized by this particular tool to solve a particular geometry, to compute electric field and magnetic field. And in terms of antenna, if I talk about, there are multiple other parameters that justifies the performance of an antenna. We would be talking about that in a short while. So yeah, FICO is nothing but a state-of-art tool which conducts computational electromagnetics, which helps us to compute computational electromagnetics depending over some frequency domain techniques, depending over some time domain techniques. And this particular tool is being utilized in vast range of antennas, in placing the antennas over a suitable position or over a suitable platform, in creating multiple microwave devices. When I say microwave devices, then these are the passive devices that you people work on in third semester, in fifth semester or sixth semester of your engineering programs, where you might have seen some directional couplers, you might have seen some isolators, some power dividers, some microwave T junctions. So these are the microwave devices. And last but not the least, this particular tool can also be used in bioelectromagnetics. When I say bioelectromagnetics, that it clearly means that biological concepts are to be characterized through electromagnetic waves. That means so you all are using the smartphones, right? And every smartphone has some impacts over the human bodies. Higher the usage of the smartphone, larger will be the impacts of the radiations that are coming out from the smartphone over the human body. So this particular study we people do in terms of specific absorption rate ratio. Specific absorption, we people calculate. Every mobile has a specific absorption, and if you want to check it right now, you people can just dial star hash 007 hash. Just dial with your Android phones star hash 007 hash, and you will be having some SAR values of the mobiles. So generally, as per the IEEE standards, as per the government norms, if it is larger than 1.6 watt per kg, 1.6 watt per kg, if this particular value is larger, then you need to switch your mobile phone. You need to change the handsets, right? So moving further, over the tool, we have multiple computational electromagnetic methods that categorize the problem statement. The problem statement could be of a single antenna, could be an array of antennas for the Wi-Fi routers, could be an array of antennas for the 5G, which includes multiple number of elements. Very large number of elements are to be there over a particular 5G antenna. So depending on the problems, we have different numerical techniques, different computational methods that can be utilized. I'll not be going into this detail because this would be very advanced for this particular topic that I was told by Professor Shah. So these are the multiple methods that we people use depending over our requirement and depending over the complexities to a particular problem statement. So multiple solvers, the pairing of the solvers can also be done, and the cables can also be included. So these are the particular solvers that we people use in this particular tool. Moving further with this tool, with this particular electromagnetic tool called FICO, where we can go, what else we can do. So in electronics and telecommunication engineering sector, we people can work on multiple antenna arrays, multiple antenna, basic antenna designs, placements, electromagnetic impacts over a object, over a instrument, equipment. Due to the presence of other equipment in the close proximity, we people can check it. So depending over this, we people can work in electronics and telecommunication engineering domain. Then aerospace industry, we people can work on RCS computations. RCS is nothing but the measure of the detectability of an aircraft by the enemy's radar. If we are in the flight mode, how our aircraft, how our aeroplane can be detected by an enemy's radar is measured using RCS. So lower the value of the RCS, lesser will be the chances of getting detected. So this sort of things we people can do in aerospace designing and in aerospace sector. In defense sector, again, we people can create some directional antennas to be used in a particular directions For different applications, we people can use antenna arrays. These antenna arrays can also be placed over the aircraft, over the missiles for a better guided variations. So all these things we people can do in defense sector. In naval applications, again, RCS is one of the major factor, one of the major application where people are using this particular tool. RCS, lightning strike, electromagnetic interference and compatibility, antenna designs, because everywhere you talk any path of the life and antennas are there. Either it is your smartwatch, antennas are there. Either it is your mobile phones, antennas are there. Either it is some television coverage, mobile phone is antennas are there. So any path of the life, antennas are playing a very massive role. So we people can use this particular tool in any sector. In railways, again, anti-collision radar is one of the major applications where people are using this particular tool along with antenna placements and EMI/MC applications. In electric vehicle sectors like automotive sectors, where there are multiple cables, there are multiple circuits that are lying over an electric vehicle, so we people can communicate, can create such scenarios. We people can create car-to-car communication using this particular tool. We people can create the scenario for wireless charging of the equipments and everything in electric or automotive sector. We people can do with this particular tool. Last but not the least, bioelectromagnetics, as I was talking to you in terms of a specific absorption rate ratio, we people can calculate, we people can perform MRI scanning, virtual MRI scanning of a human body, we people can do here in particular tool FICO, up to 7 Teslas, we people can do this. Moving further, so these are the summarized applications of this particular tool. Few of the wire, moving further, few of the wire antenna class, like few of the helix antennas can easily be created, few cross-coupled dipole antennas can be created, few Yagi-Uda antennas, log periodic antennas. These are the class of antennas that you people know easily, like you people have heard about these antennas in your textbooks. And then few microstrip antennas and some conformal antennas, microstrip patch antennas you people might have heard of. Patch antennas are nothing but a metallic surface is lying over a dielectric surface. This is nothing but a patch antenna. So the modifications in this particular class of antennas are being done in terms of making it conformal, in terms of making it circularly polarized, in terms of making it reconfigurable. Multiple higher advanced applications are there for which this particular patch antennas, basic patch antennas are being used. Then we have some small printed UWB antennas. UWB is nothing but ultra wideband antennas, excuse me. Ultra wideband antennas can also be possible with this particular tool. So as I was saying, that there are massive number of antenna class which we can categorically use as per our applications. Then a few class of antenna arrays, like an array is nothing but a number of elements of a similar class or similar domain. So a single unit element can be created and that can be converted into a array, either a square array, rectangular array, circular array, anything, whatever we want to do. And this can be easily handled with this particular tool. Then you might have seen the Tata Sky dish. You might have seen the Airtel dish. So these are nothing but the reflector antennas, right? So these are the reflectors. So these sort of reflector antennas can also be tested, can also be created using this particular tool. Then few of the antennas that are created for electric vehicles, that are created for aerospace engineering, where in aerospace engineering, some is working for VHF, UHF band frequencies for a particular capturing of a particular application. So these antennas can also be placed over some vehicle, some aircraft, some ship, and the antenna placement analysis can also be done. Like in this particular case, this one is nothing but a satellite. I have the pointer very quickly. Yeah, this one is nothing but a satellite over which a array of the antennas has been placed, and the impact of the array of the antenna over the satellite part has been tested, where a helicopter was used for which a monopole antennas have been used over this helicopter, and the impact of that particular antenna is being visualized over the helicopter and the commercial aircraft. Commercial aeroplane has also been used where a VHF monopole antenna has been used over this particular bottom position of the fuselage, and this particular case has also been tested. So depending over your requirement, you people can use the tool. Few more examples of the antenna placement over aircrafts using different numerical methods. Few examples in terms of RCS computations, like radar cross sections. As I told you, it is nothing but the measure of the detectability of our aircraft or object due to the presence of an enemy's radar. So these things we people can do. Few circuits like some couplers, some spiral microstrip circuits, some filters. All these things can easily be created using this particular tool. Another class of array antenna array, where slotted waveguide structures are being used to create the array, right? And this is nothing but a class of 5G application, a very beautiful demonstration of beam steering applications due to the presence of a massive number of antennas over the nose cone of the radome, nose cone of the aircraft. This is the portion which is called as nose cone. Within this nose cone, X-band weather radar antenna array has been used, and this is used to steer the beam in different directions. This is what you were seeing here, right? The beam is steered around the particular angles, right? And few cases for bioelectromagnetics, like single mobile can be tested where multiple antennas has been used. So how the impacts of the antennas that are being used in the mobile phones, how these antennas are impacting over human bodies, some implantable antennas, some pacemakers, some antennas that can be used to monitor the heartbeats, to monitor the temperatures of the body. These sort of antennas can easily be created. And if a human body is being placed in an electric car, so what are the impacts that can also be calculated with this particular tool. So this is nothing but just a brief introduction about the tool. And now very quickly, I'll be taking you guys to the tool, which is called FICO, and it has preprocessor and post-processor. And in preprocessor, we people create the scenarios, we people assign the inputs, and we people solve the problem. And in post-FICO, we people visualize the different results. So this is nothing but the graphic interface of this particular tool. Right, so I'll not be going in the detail of the tool or the graphic user interface. Rather, I'll be more interested to show you the designs of the class of antennas that we have just gone through. So I'll be starting with a very basic antenna that is nothing but a monopole antenna, which is nothing but a wire. Monopole is nothing but a wire. If you notice, then I have created a line. I have created a wire having certain length. Right, this length is calculated as per the lambda. You all know that monopole is nothing but a wire antenna which is having a length of lambda by 4. Lambda is nothing but it is equivalent to the frequency that is being used. So in this particular case, the frequency of interest is 125 megahertz. The center frequency is 125 megahertz, and according to what that 125 megahertz, this length has been calculated for this wire antenna. And along with that, since a wire cannot be like hang in a free space, it needs some base to over which it can stand. So this is nothing but the base of this particular wire antenna. It is nothing but it is called ground plane. So this ground plane is being used over which the wire has been created, and certain frequencies has been applied to test it. And I'll be giving you the results of this particular wire antenna very quickly. Yes, so this was my wire antenna that has been created. And in terms of antenna class, let me give you a brief over what are the performance parameters that we people use to test for an antenna, whether it is working fine or not. So the very first performance parameter is nothing but reflection coefficient. Reflection coefficient gives the measure of the reflected waves. You might have studied in terms of electromagnetic field theory, that what are the reflected waves, what are the forward waves. So all these things you might be knowing. So reflection coefficient is nothing but the measure of the reflected waves. So what are the reflections are there in the structure? So lesser the reflections, better is the performance of the antenna element. So in this particular case, if I show you the reflections, Then, if you notice that around 125 gigahertz of the frequency, my reflections are below 20%. 0.2, it is lying below 0.2. That means below 20% reflections are being occurred in this particular antenna element, and that can be considered, right? That means above 80% of the energy, above 80% of the signals are being passed in the forward direction. So, what is that particular forward direction of the antenna element in which the energy is being radiated? So, if I show you, then this is the reddish area. This is something called omnidirectional, which radiates the omnidirectional. What is omnidirectional? Omnidirectional is nothing but a coverage of the antenna element in which the antenna is radiating equally in all the directions in terms of azimuthal plane. Azimuthal plane is nothing but a part of the spherical coordinate system in which phi is being varied from 0 to 360. So if you notice, in 0 to 360, this is my azimuthal plane, and that this particular antenna element is radiating almost equally, right? So this is the radiation pattern. This is called radiation pattern. This could also be visualized in terms of the polar curves. In terms of the polar curves, yeah, this can easily be visualized. And in dBs, if you notice, this is how the radiation pattern of a monopole antenna looks like. Right, so this is one class of antenna, one class of wired antenna actually. Now the next class of antennas could be, I'll give you the other class of antennas, which would be the next wired antenna is Yagi-Uda antenna, which is nothing but an array of the monopole antennas. I'll show you that part. The Yagi-Uda antenna, the TV antenna you might be knowing. In the earlier times, over the terrace, there are some rods that has been created in order to catch the satellite signals to have a better coverage over the to have the better image over the TV. So this is nothing but the same antenna, Yagi-Uda antenna, where there is a reflector. The very left corner element is called reflector. The second element is called as feeder, and rest of the elements are known as the directors. Directors are used in order to direct the energy into a particular direction. So Yagi-Uda antenna is one of the directional antennas. That means it will not be radiating omnidirectionally, but yes, it will be radiating into a particular direction with a very much higher gain or with very much higher directivity. So if I show you that particular radiation pattern of this particular Yagi-Uda antenna that has been created for to demonstrate to you guys, then this is what it looks like. Like in the direction of the directors, it is radiating all its energy, while there is nothing in the back directions. If you try to relate these color segments, these 11 segments of the colors with the color segments in the radiation pattern, you will be able to read that in the back directions there is nothing, but in the forward direction there is the maximum radiation that is being happening with a magnitude of 13.5. Right? So this is how Yagi-Uda antenna works, that it directs the energy into a particular direction. Also, if you try to notice the reflections within this particular thing, then reflections are below 0.1. That means if I apply a marker, if I apply a global, if I try to check the global minimum, that it is 0.018. That is 1.8% reflections are only happening with this, with due to the presence of this particular Yagi-Uda antenna, and which is very much accepted. That 1.8% reflections, that means 98.2% of the energy is being directed into a particular direction. That is very closer to perfection in terms of antenna class elements. Those who study antennas, those who understand antennas, they will be giving their input that yes, this is very much higher performance of the particular antenna. Along with this Yagi-Uda antenna, there exists another directional antenna which is known as horn antenna. You might have seen some. I'll use a Hindi word. I'm not recalling it in English. Some bhampus, right? Which loudspeakers like horns. So horn is nothing but that sort of element only, which directs the energy into a particular direction again. So we'll be giving you that class of antenna very quickly. So yeah. it is somewhat very much similar to the antenna or similar to that particular antenna which is used along with the loudspeakers in some functions. So this is something that only. And if I give you the performance of this particular antenna, then again you will be doing that. Yes, it is again directing the energy into a particular direction. So larger the mouth of the horn antenna, you see. Yes. If you try to notice, you see, this is a particular directional performance of this particular antenna. So larger the mouth of the antenna, higher the energy will be radiated into a particular direction. And this is this particular horn antenna is nothing but a broadband antenna as well. Oh, sorry, it has been plotted gain. Let me plot this particular parameter which gives the reflections. So if you notice, then within this particular band of 8 to 12 gigahertz, it is having the performance of the antenna or the reflections from the antenna is lying within the range of 0 to 20%. That means within the entire band of the 8 to 12 gigahertz of the frequencies, the antenna is behaving in a better way. That means the antenna is working for the entire band of frequency, and that is why it is called as broadband antenna. Now, here you need to understand three terminologies. The first is narrowband antenna, the second is wideband antenna, and the last but not the least is broadband antenna. So narrowband antenna is nothing which is working at a very resonating frequency or which is working within a very narrow band of frequencies. Wideband antenna is nothing but which is working over a wider range of antennas in comparison to the narrow band, and broadband is something which is working for the entire band of simulations. Right? So this is something what we call a horn antenna. Why I am running so fast that Professor Shah already knows that yes, I am lagging in terms of the power since morning. I informed her, so that's what.
Yes, sir, no problem.
Yeah. So next class of antennas, another class of wire antenna here, which is called as helix antenna. So helix antenna is nothing but you might be remembering the springs with which we used to play. So helix antenna is nothing but a sort of spring, right? A spring sort of structure this particular class of antenna is having, and yes, to make a spring to stand properly, it needs some ground plane. It needs some base. So this circular plate is doing nothing but it is giving the base to this particular helix part, and also it avoids the reflections to go in the backward direction. This is very much technical in terms of the antennas, that ground plane prevents the reflections to happen. Right. So on this particular helix antenna is again very of higher importance in terms of aerospace engineering. These helix antennas are used. So yes, again, this is the performance of this particular helix antenna. Again, it is quite directional. If I show you in dBs, then again it is quite directional depending over the turns of the helix, the turns you are observing within the helix. You increase the number of turns and you will be having this sort of increments in this sort of azimuthal plane positions of the radiations. So this is a very beautiful pattern of this particular helical antenna. Right? You can have it over different frequencies as well. With the frequencies, it should vary, and it is being varied at different frequencies. If I measure it at 1 gigahertz, so this is how the pattern looks like. And if you try to now measure the colors of these back radiations, which is happening beyond the ground plane, then you will be able to see that if we try to relate the color bands with the values, then there is nothing in the back sides, in the back lobes, right? So this is one of the class of the helix antennas. These all are the classes of the wire antennas, and now we'll be moving to another class of antennas which are called as patch antennas, microstrip patch antennas we have. So a patch is nothing but a sort of dhabba, right? So this patch or dhabba could be of any shape. Either it could be square, either it could be circular, either it could be electrical, either it could be the initials of your name. Anything it could be, provided that if you are trying to create a patch of the initial of your name, then it should have that performance. Right? So I have created an elliptical antenna. I'll be showing you guys. Yeah, this is nothing but this particular part you might be seeing. This is nothing but an elliptical aperture, elliptical surface, which is lying on the top of this particular dielectric surface. This is nothing but a dielectric medium. So this is how a patch antenna looks like. And if I show you that from where I am giving the inputs, then you will be able to see that this line you would be able to see, right? This line is working as a feeder to this particular patch for me, right? This line is working as a feeder to the, of this particular patch to me. So I am very quickly jumping into the performance of this particular patch antenna. And patch antenna has some radiation patterns into a particular direction, and that direction, what it would be, if I show you that, then this direction could be easily notified, easily measured with this particular polar curve. If I try to measure a maximum point, then this elliptical patch is having a gain of 5.26, or if I measure in dBs, then this particular patch antenna is having a gain of 7.2 dBi in the direction of 5 degrees. That means the patch antenna is radiating its maximum energy in the direction of 5 degrees, and if I want to change the direction of this 5 degrees, then I can input some phase variations. From where I can input some phase variations, if I show you that part, then here in the source, whatever source we have used, we have applied a voltage source which is having a 1 volt of magnitude. This phase is something called 0 as of now. So if you make this phase 30, 45, 60, 75, 90, whatever you want to have, so you can test it, like by inputting different phase, the beam will be shifted from 5 degrees to 7 degrees or 3 degrees as per the input of the phase. So this is something we can do, we people do for different applications. I'm not talking about a specific application. That is why I am giving you a very large number of antenna class of elements. Otherwise, a patch is itself a subject of research. Like many people are doing the research over this particular patch antenna. Many articles are being published on regular basis of this particular topic of patch antenna. If I show you the reflections of this particular patch, then very quickly I'll plot a curve. So if you notice this, then if I measure the point global minimum, then this global minimum is at 2.449. That is at around 2.45 gigahertz. It is having 0.0872. That is 8.7% of the reflections are only happening from this particular tube or from this particular patch antenna. And if you try to go beyond 2.545, or if you trying to go below 2.45 gigahertz of the frequency over the curve, then these reflections are increasing. So this is nothing but a class of the narrowband antennas. This is nothing but a class of narrowband antennas. You can also check these, like you might have heard another terminology which is called VSWR, voltage standing wave ratio. If you have focused somewhat on electromagnetic field theory, there it comes, voltage standing wave ratio. And the ideal value of the voltage standing wave ratio is 1, and the worst value is 2 or above. So if I try to show you, then at 2.45 gigahertz, this VSWR is nothing but 1.19, which is very closer to 1. And apart from this 2.45 gigahertz of the frequency, it is like below 2.45 gigahertz, it is well below, higher than 2. And after 2.45, it is again well above 2. So this is what a narrowband antenna looks like. A narrowband antenna characteristic or performance looks like. Another terminology you might have studied, which is called a return loss. Return loss is nothing but the representation of the reflection coefficient in dBs. Return losses, and ideally it is said that an antenna should have a return loss of at least minus 10 dB. So the higher the lower the value of the return loss, better is the performance of the antenna. So this particular antenna is having 21.18 dB of the return loss at 2.45 gigahertz of the frequency. Right. So this is how an antenna is being studied. This is how an antenna is being judged in terms of the performance parameters. So I have covered a very wide class of antenna applications in a very short span of time. I have not entered into the tool. I have not entered into the graphic user interface just because of the fact that my system is running out of battery. It may shut down at any time. So, if ma'am, we have Professor Sharma, can you please come in? Hello, Unnati, ma'am.
Yes, sir.
Ma'am, since my battery is all about to die, I have got two notifications.
Okay,
So
okay, sir.
yeah, I have covered multiple class of antennas depending over the interest of the audience. Like I was told that there would be some polytechnic student, there would be some
Yes,
undergrad
sir.
students. So depending over their interest and depending over their the level of the knowledge they people have through their theoretical subjects, I have covered few class of antennas.
Okay, sir.
So if there is some queries for me or there, if they want to see another special class of antenna, then I can very quickly show them.
Okay, okay, sir. Just a minute. We'll just check out. Question is, uh, one student from electrical department, sir, asking about how to work helical antenna and where we um, add the helical antenna.
Like helical antenna is itself a special class of antenna. As I show you the radiation pattern of the helical antenna, then you might be noticing that it is having some sort of directional properties again. So wherever we need to have higher directivities, wherever we need to have the reception from a particular direction, we people can use helical antenna in such cases.
Okay, sir. And sir, one student from again electrical department asking about how to Yagi Uda antenna work
See,
because
the
yes.
theoretical concept of Yagi-Uda antenna is nothing. It is nothing but a pair of an array of the monopoles and the dipoles. If you try to notice the structure of the Yagi-Uda, let me give you that structure very quickly again. Yes, if you try to, let me make it a better visualization of this. Let me delete the symmetries. Yes, if you try to notice then, the second element is nothing but my feeder, which is having a source, input source is applied at this particular position. It is nothing but a dipole, but rest all other elements are the passive elements. In Yagi-Uda antenna, it is said that it is a composition of active and passive elements. Active are nothing which are having some source from somewhere, and passive elements are nothing but that are dependent on the active ones. So in out of this feeder is my active element, while rest other elements are my passive ones. So this is my reflector. The very first element in the negative of X is my reflector, which is preventing the reflections to happen from the feeder in the opposite direction. That means, and all the elements like element number third, fourth, fifth, sixth, seventh, these are the directors. Directors with the name itself, we can predict that these are something that are directing energy into a particular direction. And this is what I demonstrated. I demonstrated the pattern of this particular Yagi antenna, which is having a radiation pattern into a particular direction itself. Right? If you notice that the radiation pattern is in the direction of the directors only. There was nothing, there was something in the direction of the reflector, but yes, if you try to relate the color code, then the value of this particular reflection in the direction of the reflectors is almost zero. So this is how Yagi-Uda antenna works around.
Okay, thank you so much, sir. And because of some issues your side, so I will just give thanking you. Thank you so much, sir, for your
Thank you,
valuable
ma'am.
time and sharing information on RF antenna using EM simulator FIGO. I would like to thank you, Principal Sir, Professor Jatin Vaidya, to provide endless support and motivation to take such kind of initiative. On behalf of EC Engineering of Parul Polytechnic Institute, Parul University, I would like to thank you, sir, and all our head of department, faculties member, and students. Last but not least, I would like to thank our all students and all participants. Thank you so much, sir. Sir, you can leave. Sir, you can leave now. Hello, Karthik sir.